Hello everyone, my name is Sirin Ahmed and I am a PhD student in the Department of Electrical Engineering and Computer Science at Texas A&M University, Kingsville, United States. I am currently working as a research assistant in the Cyber Physical Power and Energy System Laboratory. Today I am going to present our team's work titled as a Blockchain Integrated Resilient Distributed Energy Resource Management System or DERMS. This slide shows the outline of today's presentation discussing about real incident of cyber attacks across the world and cyber attack scenarios to DERMS. Then proposed method is explained if traditional DERMS is failed and will be validated by the Simulink model and results. Finally, this presentation will be concluded by addressing the future works. So as we know that the penetration of distributed energy resources such as PV, energy storage systems and wind turbine systems, electric vehicle in the electric power grid is rapidly growing. Broadly dispersed DERs with advanced communication and computing systems are expected to improve the power grid resilience if it is managed securely from remote power system management systems such as DER management system or DER aggregator. Typically, DERMS is a central controller implemented in a utility server or cloud that receives real-time grid data from advanced metering infrastructure or AMI and DR system data from DR smart inverters and then sends control commands to the DR inverters and controllable switches. However, the centralized DERMS system is vulnerable to a single point of failure. Extensive studies have been done to address cybersecurity challenges in the DR system, but mitigating attacks causing a single point of failure of the DERMS has been less studied. In this slide, we will see many real cyber incidents occurred in the past across the globe. First incident of cyber attacks occurred on 7th May 2021, in which an American oil company Colonial Pipeline suffered a ransomware cyber attack by dark-side hackers. It infected some of the pipeline's digital systems, shutting it down for several days. Colonial Pipeline paid dark-side hackers $4.4 million in cryptocurrency to get the decryption key. Second incident took place this year in April 2022 where three German-based wind energy companies were targeted by the Conf ransomware group and then prompted to shut down remote control systems for roughly 2,000 wind turbines for a day. Lastly, an energy company providing power in several western US states experienced a denial of service condition that resulted in interruption of electrical system operations for more than 10 hours on March 5, 2019. The DR system architecture, which is shown in this figure, in which the utility DERMS manages the DR aggregator and facility DR controller and groups of DR, and the DR aggregator manages all the small DR devices. Cyber incidents that we have seen in previous slides can also occur in DERMS. Here we can see two cases of cyber attacks possible in DERMS. First case is DDoS attack or DOS attack, like distributed denial of service attack, that occurred at an US electric utility on March 5, 2019. A similar DOS attack is possible in DERMS if an adversary finds the firewalls of a DERMS exposed online via specialized device IP and port search tools. Then the flood of fake requests disables the network devices of the DERMS using DOS attack tools. Moreover, DDoS can directly target the DERMS server with numerous bots. Second case is the ransomware attack to the DERMS. For example, a ransomware actor can purchase a stolen credential from legitimate insiders, cybercrime partners, or third-party intrusion brokers as an initial access to a DERMS server. Upon obtaining privileged access, the actor can establish a persistence backdoor platform in the server to upload ransomware and export sensitive data. The adversary remotely can encrypt the critical files for DERMS monitoring and control, and then start to demand a significant ransom payment to restore the locked or compromised DERMS. Figure in this slide illustrates the concept of blockchain-based cooperative cyber resilient ecosystem. We can see this figure that this is the physical system layer where DER is at the grid edge, and this is the network layer, and this one is the cyber layer where the core blockchain cluster in cloud computing and peers in stakeholder servers are present. This is the multiple DR stakeholder system where we have DSO, energy market, DR owners, DR vendor, aggregator, DERMS, which monitors and control the DR smart inverter. And this one is, we can see in this multi-channel blockchain model, here we have different channels. Green color shows control channel, and blue color shows transactive energy channel, and purple is security channel. So for the control channel, we can see that utility DERMS is controlling the third-party DR aggregator or DR. And for a multi-party environment, standardizing the mutual agreement procedure in blockchain will support the multiple stakeholders moving toward a common set of effective cyber resilient grid practices. The proposed blockchain-based security governance platform will build a collaborative security ecosystem where multi-party can seamlessly handle the utility, aggregator, or vendor-identified incidents through effective notification, coordination, and validation mechanisms. All the governance functions are programmed in the form of smart contracts with mutual agreement of parties related to the functions. However, this paper assumes that the blockchain system already exists and focuses on the use of control channel for recovering a DR system when DERMS is out of service due to cyber attacks. This figure shows the proposed blockchain integrated DERMS controlled by DERMS smart contract and an overall recovery process of the malfunction DERMS by DOS or ransomware attack. In the blockchain integrated DERMS, the blockchain peers or nodes are used as a secure medium to deliver critical information among DR inverters through distributed ledgers for secure and resilient control purpose, as well as authorized stakeholders for better situational awareness. Connected to the blockchain nodes, DR sends their local measurements to the blockchain system, such as voltage, current, frequency, power, active power, reactive power, and can access the shared DR data and control commands. Such monitoring and controlling of DRs are managed by DERMS control smart contract. And once an IDS, like intrusion detection system, detects the malfunction DERMS, the DERMS smart contract will be activated. Here we can see the activating DERMS smart contract, and based on the measurement data stored in the ledger and tertiary control requirement by the distribution system operator, DERMS smart contract generates a control commands for the DR inverter. It will generate the control command for the DR inverter, acting as a virtual DERMS. And the shared data and control commands retained in the ledgers are then available to the DR inverters. Therefore, or by this way, blockchain network provides an alternative channel to the DR system on behalf of DERMS, enabling cyber-resilient operations for the DR system, such as adaptive frequency ward control and volt VAR control depending on the grid condition. The DERMS smart contract will be deactivated once the DERMS is recovered, and it will provide credits to the peer nodes. This slide discusses a smart contract defined DERMS control. DERMS smart contract consists of two parts: monitoring script that describes the rule of data collection and sharing between the blockchain network, DR inverters, and authorized multi-party clients. Control a script that is a logic statement for voltage recovery at PCC in the DR system. This figure shows the sample of a smart contract or chain code written in the Go language for the DR system monitoring. So now, to validate the proposed method, experimental setup can be seen in this figure. In one PC, physical DR system model is implemented in MATLAB or Simulink, and another PC is used for the blockchain or DERMS server. The blockchain server is designed using the Hyperledger Fabric platform, and for the interfacing, a MATLAB function block is used to establish a network interface between the Simulink model and the blockchain server using local Wi-Fi. And in this slide, the DR system in IEEE 30 node test feeder circuit is shown, which consists of multiple smart inverters, swing bus, and wind turbine, photovoltaic, and energy storage system and loads. The DR system model is implemented in MATLAB or Simulink. As an example of a smart contract defined DERMS control, this work shows a voltage restoration control at the point of common coupling of a DR system. The ESS, or Energy Storage System Inverter Control model, is shown in this figure. The primary controller controls the voltage, current, active and reactive power flow of the ESS inverter, and combination of active and reactive power calculation and droop control determines ID reference, IQ reference, and through the PQ calculation and droop control, P reference or Q reference can be computed as follows. And then this P reference and Q reference will be provided by the DERMS server and blockchain server when DERMS failed. The figure in this slide depicts a screenshot of the ledger data showing the monitoring status of the DR system, and the monitoring data includes PCC voltage and frequency, DR voltage, active power, and reactive power. The integrity guaranteed DR system data can be shared with authorized blockchain clients, including DERMS operator. Therefore, continuous situational awareness of the DR system is possible, although the main terms lost visibility by the cyber attacks. This figure shows a voltage recovery control by the smart contract defined DERMS control when an inductive load is significantly increased after 2 seconds. And this figure shows the voltage sag at the PCC caused by increased inductive load after 2 seconds. The smart contract computes and stores Q reference in the ledger, which is available to DR around 3 seconds. And using the new Q reference, ESS recovers the PCC voltage to the original value. And this figure we can see here, it shows the measured reactive power from the ESS to recover the voltage at PCC, which fully follows the reference set value, which is in red color. By this way, even a conventional central DERMS is out of control by cyber attacks. The resiliency of the DERMS has been significantly improved by integrating the PC system. In conclusion, this work introduces 2 attack scenarios targeting a single point of failure of conventional DERMS based on real-world incident cases and threat modeling approaches. An overview of the blockchain-based governance model for DR system is introduced. Blockchain integrated resilient DERMS framework has been proposed to mitigate cyber attacks targeting the DERMS by substituting the operation of DR system during the DERMS outage. Future works include designing a hardware in the loop testbed, adding more DERMS control function and intrusion detection logic in smart contracts, and finally developing the blockchain-based cooperative cyber resilient ecosystem for multi-party involved DR system. This research work has been funded by the Department of Energy, the National Science Foundation, and the Korea Institute of Energy Technology Evaluation and Planning. That's all I have for this presentation. Thank you very much.